We are live.
Exciting, I know.
Yeah. So we'll see how this whole thing works. So yesterday we started working on the packet. So why don't you pull that packet out? At the same time, have your notebook out all the time, because remember that notebook is supposed to be a book of notes that you find meaningful and that you want to have record of. Okay? And I'm going to make one slight change. You know how I told you to bring your calculus book every day? Okay? I thought about it, and you really only need to bring it on the days that the homework assignments are due. Okay? This helps you from having to lug one more book, especially if you're taking AP Biology. I heard that thing's like this thick.
11 textbooks in my locker.
Oh, here we go.
That helps.
Okay. Who's Taylor? 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 Okay. Oh, okay. Do it again then. Just listen to me. Okay. Here were the rules when it came to doing the function packet. Number one, you were not allowed to use a calculator in any way. Second, if you wanted to look up something, like you needed to know a definition of something, you can feel free to look it up. Okay? But other than that, you should be able to, at any time from this day forward, well, whenever we finish this till the day forward, that you should be able to understand and know and be able to, at will, sketch out any one of those basic functions. Okay? That's the deal here. Because in calculus, we work with the functions, and that's why you studied them all in pre-calculus. Okay? So that's the deal. All right, so I just want a couple of questions. As you were doing that, was there any function that caused a problem with our ability to do it? Yes. Okay, the general polynomial. Okay, that's good. I'll talk about that one. Okay, another one. The raised integer. Greatest integer, okay? Okay? Any other ones where it's like, how are we supposed to do that? Logistic. Natural log. Yeah. Tangent one. How about all the trig ones in general? Oh, I see a lot of head nods there. Okay. You mean you can't just draw like 17 dots on the sine function? Okay. Where those numbers come? Okay, so we're going to talk about all of these, and we'll hit them one at a time. The one that's different than all the rest is the general polynomial. So we've got something like f of x equals a times x to the nth. Is that right? Okay. Now, what I'm really saying here, what I want you to understand is in this general polynomial, okay, a and n are real numbers. Okay? This is a symbol we write for the real number set. It's any real number. So a real number is a positive number, negative number, 0. It can be an integer, it can be a fraction, it can be a decimal. It can be rational, it can be irrational. All those numbers there are real numbers. So we can kind of say a and n can be anything that they want to be. But when you graph this, there's actually some patterns that occur. Okay? And you may have done this thing last year. Right? Something like that. Okay? And it had to do on things like, well, is there any pattern when a is positive versus when a is negative? Okay, is there any pattern? And not only that, is there any pattern for when, maybe n is even or n is odd? Okay, that's what I want you to I want you to try to summarize that. So it's not really just one graph. What I'm really looking at is, can you basically give me 4 different situations for whether or not when a is positive or negative and when n is either even or odd? Okay? Put all those together so you get some semblance of that. But then I'll explore the other ones, like what if n is 0? Okay? These are kind of like extras. And what if n is not an integer? Okay? What if n is a fraction of some kind? Then what happens? Okay? I want you to just think about that, because there's lots and lots of different kinds of scenarios that can occur with this, and the functions get kind of weird. But that's good. We're into weird here. Okay, so that's that one. All the rest of these, I think we can take them one at a time. Okay. All right, so how about this in your notebook? What is a function anyway? You've studied functions for a long time. What is it? What is a function? F of x is equal to 8 times x to the nth, or like here, f of x is equal to this goofy bracket thing, and then natural log of x, f of x is equal to this ln of x. Yep. Bless you. And then you got all sorts of ones here, sine, cosine, tangent. Okay, what are these things?
Set of numbers and variables that describe a rate.
Okay, that describe a set of, say that again?
Variables and numbers
Variables and numbers
that describe a rate.
that describe a rate. Okay, I like that. Okay, they have some sort of relationship, right? Okay, anybody add anything to that, what a function is? You guys have been looking at functions for a while, right? What, do we know what they are? Or do we just do it? Well, let me see if I can describe it another way. Now, this box is no ordinary box. Okay? And the school board wouldn't let me buy a real function box, so I had to make my own. Okay? And so this box right here represents what happens in a function. Okay? So, for example, okay, the function here is f of x equal to 3x. Okay? And so what a function does is it relates an input number to an output number. Okay? That's what it does. It describes the relationship between them. For example, okay, take the number 7 and I put it into the function box. Okay? It does the operation on it. Pretty impressive, hey? And it performs the operation, and there it is. Okay? And what's fun about it is you can put in any number that you want to. Okay? You can put any number that you want to as long as you can, you're allowed to, and out pops the number. Okay? Like that? And what's cool is we then discuss, in order to work with this, we give them fancy names. What are the numbers, what are the set of numbers called that go into? Well, we call them, we normally have x because it's f of x. X is the function. Do we have another name for those that go in? Domain. Every one of the numbers that go in are the numbers that are in the set of the domain of the function. Okay? The numbers that come out are called the range. Okay? So you have a set of numbers that you can put in, you get a set of numbers that come out. And they have a fancy name as the domain and the range. Okay. Well, let's see how flexible this thing is. So we'll give it another function. See if it can do the work. Okay. So everybody see the function? Okay. Let's put it in a number. And what comes out? Isn't that incredible? It's just amazing. All right, let's see how good it is. There we go. Plug it in. Come it out. Okay? It's just amazing. Okay. So, and let's see if we can do a hard one. Okay. All right. Last function. Here we go. Input, this is the domain. Okay, this is a number in the set of the domain. And outcomes, there. Is it right? It's amazing. Okay, we plug in one more. Okay, we plug in one more. And out comes. Okay. Now, what's really crazy, if this is the output, and then you put it in. Okay, I put in the output. What comes out is a Tootsie Roll. Who knew that? And the number 12 is a magic number because every time you plug a 12 in, out comes a Tootsie Roll. Tootsie Pop. Tootsie Pop. It's just, I don't know why it works. I just love it, and I do it all the time anytime I'm hungry. So, all right, that's the function box. Okay? So, the deal is we have this huge set of functions that we need to know, and it has all of these have the same features. So, for example, let's do greatest integer function. Okay, and so f of x is equal to the brackets. Okay. Now, the greatest integer function is one of those special functions that has a certain definition. Okay, I looked it up online just to make sure that we were all on the truth. So you can just trust me on this one. Here's what I read. It was on Wikipedia, so I know it's true. It said that if you input a number in the greatest integer function, what it does is it finds the greatest integer that is less than or equal to the number that we put in. I'll say it again. When you plug in a number into the greatest integer function, that's the input. The output is the greatest integer that is less than or equal to the number that you put in. Okay? So, if we talked about domain and range and all that, then we can make a t-table, and we'd say, all right, I'm going to put in some numbers here, and I'm going to get out some numbers here. Okay? So see if this makes sense. If I plug a 2.3 in, according to that definition, what am I supposed to get out? A 2. 2 is the greatest integer that is less than or equal to 2.3. Yes?
For any of these functions, can you use like any of the numbers?
Yeah.
Okay.
Yeah. Any number, as long as it's legal to put it in here. And we'll talk about...
Like, well, there is a couple that has like less than.
Yeah. Like, can you put in, let's assume this. Can you give me a function where you're not allowed to put any number in? It's illegal. Like, the whole function box blows up. put a real number in. Yeah, if you didn't put a real number in, well, then we'd have issues anyway. Okay? Come on. Think of a function that you're not allowed to put a number in.
It's not.
Function of x is x over 0.
Keep thinking. What did you say?
I said imaginary.
Imaginary? We're going to stick to the real number set.
F of x is equal to 1.
Oh, okay. Let me see. If I have a function and f of x is equal to 1, okay, can I put in any number that I want to? Stop and think. Yes, I do. But what's the answer? It's always going to be 1. No, it's Pay no attention to the board. So if I have, so f of x equal to 1 doesn't follow that rule. You can still put any number that you want to into it. Okay, you can get any x, but the output is always 1. Okay?
You can't have a function.
That's a good question. Is that true? Say the question again.
The question?
Yeah, what'd you say?
Well, you asked if you can have a function that doesn't have an input. And I would say no, because then you just like you wouldn't have a function if the function had like an input and an output. They can be the same or different, but you can't have an output.
Okay, this is good. We've got something on the table, and this is how this class works. Now it's time for discussion. Is it possible to have a function where there's numbers that you can't put in?
The
Square
square root function.
root function. Like George, I think we've got it. That's a gold medal. Okay. So square root function. Okay. Pretend I've got the square root function in here. Okay. What kind of number can I not put in? I can't put a negative in. Because when I put a negative in, it doesn't give me anything out. It's undefined. There's no value that comes out. You see? So that's an example. The square root function is an example where you can have input, okay, but for these, we say it's undefined. There is no value. Which is why in the square root function, general graph of the square root function, square root of 0 is 0. Square root of 1, 1. Square root of 2, it's about 1.4. Square root of 3, it's about 1.7 something. Square root of 4, 2. Feel free to jump right in there when you can. Okay? So, square root of negative 1, can't do it. It's an imaginary number, but the deal is our coordinate plane, which maps our x-axis with our y-axis, are both real number lines. They're not imaginary lines. Okay? That gets into the whole complex number system set, and we're not going to do that in this class. So, when you say the domain is restricted, like on some of yours, on this one, you would have said that the domain is, say, like 0 to infinity. And we're going to use the bracket parentheses notation all year. Okay. The domain for this means that I can plug in any number starting at 0 and going up to, but not including infinity. Okay. So that's the deal there. Does that make sense? Okay. And this is the kind of class where shoot your hand up if you're still thinking that I'm saying something wrong, or you're disagreeing it, or you got a question. Okay. That's how this works. This is true learning, right? Okay, so back to here. So 2.3 I can put in there. Can I put a negative number? What is the greatest integer that is less than or equal to negative 3.5? Negative 4. Okay? Okay, because it has to be greater than. So, what do? Well, once we have a whole bunch, then we can start to plot this. That's a scary close-up. Okay, so f of x is equal to the greatest integer function value of x. And we start to graph. Okay. So we plot a few points. And so we have a general feel, and we understand what's really going on. Okay. So let's put some points on here. So absolute, our greatest integer function value of 0. 0. Remember, the rule was, the definition of it is the greatest integer that is less than or equal to the number that I input. Okay? All right, let's go halfway between at 1/2. 0. Okay, so input and output. 1.9. 0. Okay? It's not until I actually hit at 1 that I plot an output value of 1. And the way that the mathematicians came up with an agreement of how we're going to do this is we put an open circle here, which means we can include all of the numbers up to but not including 1. We can get as close to 1 as we possibly can, but just not 1. Okay? That's when we plot here. Do you see then how the graph of this is going to go here? Okay? And it's going to hop and so on. And it goes on. That's why this is called a step function. Okay? It's under the family of functions called the step function. Now, you can follow the pattern, and you can say, well, that's why this is going to go here and then here. But you can also test. Okay? Negative 1.5, the greatest integer less than or equal to negative 1.5 is negative 2. That's why we plot the negative 2. Okay? I don't know about you, but this seems pretty worthless. I mean, whoever uses a graph that looks crazy like this? What a joke. You know, that's so typical of math. Isn't it? They make you learn these obscure things, and they define these things, and then they say, this is really important, so just learn this. Okay? Is this good for anything? I measure things on their value based upon if they're useful or not. Okay? All right. Megan, how old are you? 17. How old are you? 17? Okay, that's pretty freaky. How old are you?
17.
Whoa. Okay. You guys were all born at the same exact moment. That is unbelievable. I mean, the odds of that in this class, they have to be like 1 billion to 1. How old are you?
17.
Yeah. I bet you that's going to be one awesome 18th birthday party. What am I getting at? Yes?
When you're dealing with numbers that are usually integers like age or how many objects you have, you're going to want to use the greatest integer because you can have like 2.5, well, like items.
Okay. With the first one, let's relate it to the age. What is the point about the whole age thing and the greatest integer function? Yeah.
If you're 17, you're 17 all the way up until the point that you turn 18 that one day.
That one day is when you jump the step. True? Okay? It's at that precise moment that you jump. you've actually been using a step function your whole life when someone asks you how old you are, okay? Unless the thing is, when kids are really, when a new mother is telling how old the child is, 7 days, and then it's 32 days, or it's 2 weeks, or 5 weeks, or whatever, and then you finally get to the year thing, and then it's like, no, my son is 1,700 months old. No. So, I don't even know if that's possible. How old is that? So, all right, so this is that. All right, so that's one example. Okay, can anybody think of another example? Is this thing practical in any way? Anybody here have a cell phone? Okay. How about the data plan for your cell phone? Okay. Do you pay for every single individual megabyte that you use? You probably don't know because you probably don't pay for it. Ask your parents. They'll know. Okay? What happens is it goes, you normally pay, like we pay a certain amount for, I don't know, I'll just make something up. It's around $60 a month, but then we pay like $10 per gigabyte after that. And as soon as we use we branch into a new gigabyte, then we get paid. So when you stop and think about that, what I really have is a function, it's a cost function, in which I pay $60, okay, plus I pay $15 for every increment of data that I use. Okay? So the graph of this, when you stop and think about it, if I never use my phone at all, it sits in the drawer, I still have to pay $60, don't I? Okay, automatically. But then if I go over the 1 gigabyte that I have for my usage, then bam, I go up to the next level. You follow me? And then it's every single time I venture over to it into a new gigabyte of data, bam, I'm going up to a next level. This would be $75. That make sense? Okay, so greatest integer function actually has a lot of practical uses. Postage. Anytime you mail something or send something, think of it, if you buy something from Amazon, they don't just look at the exact weight and then use a linear function to determine how much that you owe. No, it's categories. If it's between 0 and 3 pounds, it's this. If it's between 3 and 6 pounds, it's this, and so on. You pay different prices for different things. Yeah. This one is actually called a floor function. Okay, it's a step function that's a floor. There's actually another one called the ceiling. And this is the ceiling. Okay, we use the ceiling. And the actual technical notation, I would encourage you to look it up. The floor one looks like this. Okay, because it's got the floor. Okay. And then the ceiling one, looks like this. And what it does is it fills in the other circle. Okay? It goes up versus down. And the greatest integer is a modification. It's technically the floor function, step function. Good question. Is that gold medal worthy? Okay. All right. But that's the deal. Okay. So what I want you to do, in addition to doing the learning that you're doing on the different functions, what I want you to do is think about where can this be applied? Who on earth would use this kind of thing? Okay, because that really, really helps out in the long run. All right, I'm going to give you the rest of the class time to work on the packet and compare answers with other people, try to get a little bit further on it. I can see us going the next several days on this, all right? Because we got to do all the trig functions, the natural log, blah, blah, blah. So I'm kind of anticipating us spending the rest of next week until we actually wrap up this whole thing. In the meantime, I still want you to be working on page 8 out of the homework assignment. Remember that one? That's just a review of stuff that you did before. So be cranking that out, and I'll take a couple of problems like that on Tuesday. Okay? All right. Go ahead and work in the time remaining.